All right, cool. So let's move on to the next slide, page 18. Given the equation, graph the quadratic function by transformation. We're going to start with our parent function, which was just the y equals x squared basic graph that we did. And then we're going to apply each of our transformations to it. Okay. So first step, we're going to identify the transformations, and then we're going to graph it. Looking at this problem right here, I'm going to start with the transformations to my vertex. My vertex here is going to shift 4 units to the left. Oh, sorry, to the right. Remember that horizontal shift right here is the opposite of what you expect. So since it's a -4, we go 4 to the right. And I also have a vertical shift of 3 units, and that'll be 3 units down. All right. So I do not have any stretch or compression, and it's not flipped over the x-axis, so that's going to be it. So now I can take my pencil. I know that my vertex originally was going to be at the origin, but now I need to shift it 4 units to the right and 3 units down. Get my point right there. Erase my original point just so I don't get confused. Then I'm going to come right 1 and up 1. I have a point right there. Then I'm going to come again from my vertex. I'll come right 2 and up 4. I have a point right there. So remember our original graph. If you flip back on the front page, from your vertex to find your other points, you went right 1, up 1. And then from your vertex, you went right 2, up 4. I'm doing that. How did I get my vertex? Yeah, I applied these transformations to it. 4 to the right and 3 units down from my origin. Get the other points? It's just a pattern. The pattern is this. If we don't have a vertical or a vertical stretch or compression, from your vertex, you're going to go right 1, up 1 for your first point. And then for your second point, from your vertex, you're going to go right 2, up 4. Why is that? That's a good question. Here's why that is. Let me cross this off for the time being, just to explain. Our basic function is y equals x squared, right? So if I put a 0 in for x, what's my y going to be equal to? Y is going to be equal to 0. 0 squared is 0, right? So let me make a little table here real quick. I got x, I got y. If I have a 0 in for x, 0 is my y, right? If I put a 1 in for x, what's my y going to be equal to? Yep, 1 times 1 is 1, right? If I put a 2 in for x, what's my y going to be equal to? It's going to be equal to 4, right? So if x is 2, y is equal to 4. And I'll just do one more. So if I put a 3 in for x, yep. Y is equal to 3 squared, that would be 9, okay? So again, looking back at my original graph, my first point is at the vertex, that's at the point 0, 0. My next point is at the point 1, 1. And my last point, or my third point, is at the point 2, 4, and then I could go on from there. So that's the pattern you're going to follow. No matter how you change your vertex, you count out your points in that manner. Unless there's a stretch or a compression, and then that changes things. Does that make sense?
Yeah, I didn't see anything. I couldn't see anything. They were blocking my screen.
Okay. just know that this does not have to do with this problem, right? I'm just explaining the general pattern for finding points. Good to go? Okay, so back to this graph right here. I've got the right side of my parabola down. To find the left side, I essentially just need to reflect all of these points over the vertical line that my vertex is on. This is my line of symmetry right here. The equation of that line is x equals 4. The way I know that's my line of symmetry is that's where my vertex is. So I'm just going to reflect them. Instead of going right 1 and up 1, I go left 1 and up 1 for that point. Instead of going right 2 and up 4, I go left 2 and up 4. And now I just connect my points. And that is my graph of this function up here. Took the parent function and shifted it 4 units to the right and 3 units down. Cool. Any questions? Okay, great. So looking at this next one over here, I'm going to start with my shift of my vertex again. So let's start with our horizontal shift again. This time it's a +4. I know my horizontal shift is whatever is the opposite of what I expect. So since it's a +4, I'm going to shift it left 4. I have a vertical shift of +3, so that's going to shift it up 3. And I have a negative sign out in front that's going to flip it or reflect it.
Maybe I just write inverted parabola.
Okay. Over the x-axis.
The inverted parabola.
Or to invert it, sure.
That's how I write it.
That's fine. Okay. Yes. It means that it's going to shift and it's going to be upside down. Okay. So I'm going to start by plotting my vertex. Start here at the origin, but I need to shift left 4 and up 3. So there's my new vertex. I look for my reflection next. In this case, I know that it is reflected, so I know I'm going to be coming down for my next points. I look for my stretch or compression. I don't have any stretch or compression this time, so it's going to follow that same pattern. From my vertex, I'm going to go right 1 and now down 1. And then I would go right 2 and then down 4. Again, from my vertex, I would go left 1 and down 1. And then left 2 and down 4. Okay. And that is the graph of this function right here.
So are all of them going to be the 1, 1, and then the 2, 4?
That's a great question. Nope. If we have a compression or a stretch, that's going to affect that pattern.
Because then it's going to go down or up that many times.
So we'll get there with the next example problem. We'll see that for the next one we have a stretch. And so we're going to multiply our vertical change for each point by 3 because that's our stretch factor.